So the other kind of special sequence, and therefore eventually series, that we're going to have would be one that is considered geometric. Since the arithmetic sequence basically handled our two different basic possible math operations of adding and subtracting, whether our common difference was literally positive, adding, or if it was negative, subtracting, the geometric series would account for multiplying or dividing. So if I start with a number and I multiply, or I could say divide as well, I multiply or divide by a fixed number, I can move to a second value. So again, look at the relationship that we've got here. If I move from a 1 to a 1/2, what would I have to multiply by 1 in order to arrive at a 1/2? So that particular number, would it be multiplied by 1/2 to come up with the next one, 1/4? Again, we'll talk in just a minute how that's working out. To be a 1/2 times by 1/2, I get a 1/2. Take 1/2 times the 1/2, I get a 1/4. Take the 1/4 times 1/2, I get a 1/8. I could go to the next term. If I take the 1/8 and times by 1/2, I would get 1/16. I could have also picked to times by a whole number, like multiply by 5. I could pick negative numbers as well, whether those negative numbers are whole numbers, fractions, decimals. Actually, it doesn't matter. The key thing is I'm multiplying by a fixed number. That's probably the easiest way to say it, rather than worrying about the division aspect as well. Let's just call it I multiply by a fixed number. We call that fixed number now a common ratio, because this is based on multiplying and dividing. So, got to use the appropriate terminology here. So a common ratio, there's a fixed number that I'm going to multiply by. It could be a whole number, it could be a fraction, it could be a decimal, it could be anything at all. It could be positive, it could be negative. The fact is that once I have that number, it's fixed. And to move from term to term, it's multiply by that thing, multiply by that thing, multiply by that thing, multiply by that thing, again and again and again. So, again, we can come up with a relationship based on this particular sort of pattern, that we have this fixed number, this common ratio, and moving from our second term to our third term to our fourth term and so on, we have a way of being able to refer back to whatever our first term is, and just to try to be a little bit more direct, we'll just call that A. We can refer to the common ratio, R. We can refer to whatever term we might want, so that would be the N, as usual. And this gives us that relationship that we would need for this particular special kind of sequence and eventually series. So coming to this one, we said moving from 1 to 1/2. If just we look at that and go, well, that's pretty nice. I'm going to start with a 1. I want to generate a 1/2. I'm going to do it through multiplying. 1 times what number? 1 times what number is going to give me 1/2? 1/2. Well, that means that now I can go ahead and come up with a generic formula for this particular sequence. My first term is a 1. My common ratio is a 1/2. And if I was really feeling frisky, I could say, you know what, I can tidy that relationship up a little bit using my rules for exponents. A 1 raised to any power is just going to be a 1, so that's not complicating anything there. And that means that I could just have my 2 down on the bottom with that power of n minus 1. And that gives me a slightly tidier looking relationship to use. So if n is equal to 2, 2 minus 1 is 1, 2 to the power 1 is 2, 1 over 2 is my term, check. If n is equal to 3, my third term, 3 minus 1 is 2, 2 squared is 4, 1 over 4, check. When n is equal to 4, 4 minus 1 is 3, 2 to the third power is 8, 1 over 8, check. And I could keep on going, but again, we verified that we've got the right thing. It's matching with the values that we have, so we can feel good about that. 7 over 9, 7 over 27, 7 over 81. We're being told it's a geometric sequence, so thankfully they're giving us a little nudge already in the right direction, but we still want to come up with our formula. And our formula is going to use the first term, and our formula is going to use that common ratio, so we're going to have to come up with those. Well, the first term at least is something we can directly pick out, 7 over 9. The common ratio is going to show up when I take the first term, 7 over 9, multiply by that common ratio, and get my second term. Well, since I don't know the common ratio, I do a little bit of division and come up with a way of calculating that. First term needs to be divided into the second term. So in this particular case, that means that we've got a 7 over 27 being divided by a 7 over 9. And so we come up with a common ratio of 1/3. Between the first term, 7 over 9, and the common ratio, 1/3, we can create a formula for our particular sequence. The first term is 7 over 9. The common ratio is a 1/3. That would be in parentheses and raised to the power of n minus 1. Again, we can use our rules for exponents and come up with a 1 on the top and a 3 power of n minus 1 down there on the bottom, still with the 7 over 9 out in front of that. But 9 can be written as 3 squared. Excuse me. So let's do a little tinkering here. 3 squared. Let's also go ahead and multiply across in the denominator and in the numerator. And then again, using our rules for powers, let's go ahead and write in that extra step just as a little reminder. Using our rules for powers, when we multiply things together that have the same base, that means that we can add those powers together, and that would give us a simplified formula with a 7 on the top and on the bottom a 3 power of n plus 1. That's a long way to go to get that kind of relationship. Again, if we're allowed to stop a little earlier, like right here, with a direct use of our basic formula, then wonderful, we can go ahead and stop there. That's perfectly useful to us, and with our calculator to help us crank things out, that's fine. But if we're asked to fully simplify things, then we would need to come up with something like this. And in fact, you might say to yourself, there might be a quicker way for me to come up with that, because maybe I'm just good at recognizing patterns, and I see that all of these in my sequence have 7s on top. So my formula is just going to have a 7 on the top. On the bottom, 3 squared, 3 cubed, 3 power of 4. That particular pattern would have a 3 with a particular power on it. Since the very first power is a power of 2, and my first term is literally a value of n equals 1, it seems like I would be able to take my term number, n, add a 1 to it, and that would give me the power for my denominator. Second term, add a 1, and it gives me the power that I would need. Yep, that checks out. Third term, add a 1, that gives me the power that I need. Yep, that checks out. So I might have been able to come up with that a little bit more quickly, simply based on having honed a little bit more of my skills at pattern recognition. So this is an option, but we at least have a definitive way of coming up with that formula by using our generic result here. And again, that's only going to work for our geometric series, or excuse me, geometric sequences. We're not ready to get into the series yet. Mouth. Now, geometric series can end up being a little bit more fancy in the way that they appear. And we kind of see that a little bit with that previous example. That previous example has a result that simplifies into a form that's different looking than our basic generic formula. And this is another example where we have something that's different looking from our basic generic version of a geometric sequence formula. But we're being told that we need to determine the common ratio, which means this is going to have to be a geometric sequence. They wouldn't ask us for a common ratio if it wasn't. Instead, they would have asked us first, is it a geometric sequence? And if it is, find the common ratio. So just by the nature of these instructions, this is a geometric sequence. We're gonna have to find the common ratio. Well, all right. Might help us to actually go through and look at several terms. Well, they've actually specifically instructed us to do that even before we determine that common ratio. So plugging in a 1 for our n would make a -1 with a power of 1. It would make our 2 have a power of 2. And it would make our 3 have a power of 2. And that would give us the value -4 over 9. Plugging in a 2 for n would give us a -1 squared. It would give us a 2 with a power of 3, and it would give us a 3 with a power of 4. So that means that we would have a positive term here, 8 over 81. Plugging in a 3 means we would have a -1 with a power of 3, a 2 with a power of 4, and a 3 down in the denominator with a power of 6. So this would give us another negative term. 2 to the power of 4 is 16, and 3 to the power of 6 is certainly not something I'm doing without a calculator. 729 it is. And finally, with the fourth term, when n is equal to 4, that means our -1 will have a power of 4, our 2 will have a power of 5, and our 3 will have a power of 8. So this will give us a positive term in this case. That would be a 32 in the numerator, and down in the denominator, again, I'm going to fall back on my calculator, 3 to the power of 8, 65, 61. So, we've established those four terms as we first were told in our directions to do. Now, secondly, the common ratio. The most direct thing for us, like we saw in an earlier example, is to take our second term divided by the first term. And so in this particular case, that would mean that we would be looking at the 8 over 81 divided by the -4 over 9, and that would end up getting us a negative common ratio, and that would be a 2 over 9. So, let's check that out. Negative times a negative is a positive. 4 times 2 is 8. 9 times 9 is 81. Positive times a negative is a negative. 8 times 2 is 16. 81 times 9, we can double check, that would be 729. Negative times a negative is a positive. 16 times 2 is 32. 729 times 9, we can verify, is 65, 61. So, with a little extra thought about how everything works there, we can verify that we've done that correctly. So there we go, there's our common ratio. A little bit more squirrely because clearly we can have more fractions that show up, and we have those powers that end up being important, so we may end up needing to use our rules for exponents here and there to be able to do some simplifying work along the way, whether it's working with numbers or if it's simplifying an actual formula. But still a very basic relationship here that we have established. We're going to multiply by a fixed number. Okay. Again, that could be anything. In this particular case, it's a negative. And so far, all of these have been fractions so far. That doesn't always have to be the case, but let's go ahead and segue into the series, and we'll start to see how some things are a little bit friendlier than others. And if we come back to that first example that we had used, the sequence that ran 1, 1/2, 1/4, 1/8, we had said our first term is 1, our common ratio is 1/2. And if we're asked for the 10th partial sum, what we actually have, and kind of without, creating some sort of amusing story or show you how it works out, let's just go ahead and say, here's the formula for how this works out, and let's just leave it at that for now. If we want the 10th partial sum, that means we're adding up the first 10 terms, so n is equal to 10. And the formula that we have says we still are going to use the first term. The common ratio appears in two different spots. It appears in the numerator, it appears in the denominator. When it appears in the numerator, it has a power of n, and in the parentheses, 1 minus. Down in the denominator, when that common ratio appears, it's just a 1 minus that common ratio. So in this particular case, we plug in the appropriate values in their respective spots, and then crank out that particular answer. So let's do that, though, with a different partial sum, the 20th partial sum instead, s sub 20. 20th partial sum means I would still use the same first term, still use the same common ratio in both of those spots, but now I've got a power of 20 showing up there. So what we could do is we can tweak things a little bit. I have color-coded that top set of parentheses in blue. There is a way for me to be a little clever about what I come up with so that I can try to use my calculator to the most advantage. In order to add and subtract fractions, and that's what I see here in that blue set of parentheses, I would need a common denominator. Now that power of 20 goes down there to that denominator of 2, so my common denominator would be a 2 power of 20. That means that inside that blue set of parentheses, the 1 right here would be rewritten as 2 to the power of 20 over 2 to the power of 20. So 2 to the power of 20 over 2 to the power 20. Minus up on top, shaboo. This numerator, 1 to the power of 20 is just a 1. So there's a little fancy footwork there that's going to allow me to use my calculator a bit more effectively. The stuff here in green, color-coded for a reason, that we're going to get 1 minus 1/2, that's 1/2. Because we're dividing by a fraction, that really is multiplying by the reciprocal. Keep, change, flip. Keep, change from a division to a multiplication, flip that 1/2. Well, in green, I'm going to write the reciprocal of 1/2, which would be, and I'll just go ahead and keep it literal, 2 over 1. Now, I can also be a little bit clever. 2 to the power of 20 minus 1 for my numerator. 2 on top, 2 power of 20 on the bottom. That means that there's a little reducing that would take place and give me a 2 power of 19 down there on the bottom. And Now I can go ahead and crank over to my calculator and see what that calculator can do for me. 2 power of 20. Woo! Now subtract 1. 104,8575. 104,8575 would be that numerator. Back to the calculator, the denominator would be 2 power of 19. 524,288. 524,288. Now, I mentioned this. Let's try to do this the way that it originally looked. We had that parentheses, 1 minus, parentheses, 1 over 2, parentheses, power of 20, close parentheses. That was the numerator. That was the numerator. Then we would have to divide by, and let's just say that we were typing it in without any sort of friskiness. The denominator had parentheses, 1 minus 1/2, close parentheses. And what the calculator cranks out there, hoobity-doobity-doo. We can try to use the calculator features of converting that into a fraction. So let's try to use that. That would be in our math menu. And that very first option, convert to a fraction. And then we want to hit enter to see if it'll actually do that. And it didn't. Those numbers got a little bit too big for the calculator to work with and actually transform that decimal into the fraction. That fraction was back to the notes. That fraction was, in its exact form, 104,8575 over 524,288. That's an exact answer. The calculator wasn't spitting that out, even when I tried to be a little bit clever about using calculator features to come up with that, trying to convert a decimal answer into a fraction answer. The calculator has limitations. If we, in fact, had been asked for an exact answer to this, we would have needed to use our little bit of cleverness with remembering how to add and subtract fractions, using a common denominator, using a little bit of our rules for exponents to try to reduce things a tiny bit and be able to individually work out calculations that allowed us to get our numerator and our denominator separately. So a little side note there. Again, there are going to be times where we have to worry about the limitations that our calculator, or any tool really, might have to it. But there might be ways of still using our tool to our advantage, even though we can't do it in quite so direct a way. We might be able to do it in a clever and still fairly direct way. Now again, I just wanted to torture you a little bit with that sort of thing. Most of the ones that you've got going on should be pretty manageable with the calculator. You shouldn't have to do a whole lot of fancy tinkering in order to come up with the answers that you need. So again, we're going to look at something fresh here. We got the 15th partial sum. We have a list of terms here, so we would need to recognize the first term. We would need to recognize the common ratio, which comes from the second term divided by the first term. And in this particular case, that would be 3 over 2. And they've asked us for the 15th partial sum, and that means n is equal to 15. So we have our formula. We're going to go ahead and put our values in there. The first term is a 2. The common ratio is a 3/2. The power that we need is a 15. And then back down in the denominator again, using that common ratio. And let's see if our calculator can actually handle something like this. So we can go over to the calculator and we can try it out. 2 times parentheses 1 minus parentheses 3/2 parentheses power of 15 close parentheses. That's the numerator. Divided by parentheses 1 minus 3 over 2 close parentheses. That's the denominator. enter. There's that decimal, and let's see if it'll actually convert that to a fraction. Oh, thank goodness. 143, 16139. 143, 161, 39. Over top of 8192. Now, yes, it is very fortunate that our calculator does that for us. Let me very quickly show you the little bit of tinkering that you can do with this to kind of do it out like the previous example with its clever little rearrangements. We need a common denominator here. 2 power of 15 would be what we would need. So inside that set of parentheses, we would have a 2, a power of 15. Down on the bottom, a 2, a power of 15. So this would give us our number 1 from inside of that first set of parentheses, minus, well, the second fraction already has that 2 power of 15 in the denominator, but in the numerator, 3 power of 15. So we would have that going on for our first set of parentheses from that numerator. Divided by, well, not divided by, times by 1 minus 3 over 2 would be a negative 1/2. I would want to take that and do the reciprocal, and so again, I'll just be literal about that. Negative 2 over 1. So if I go through and I do this, I can do a little bit of simplifying here, where I've got a 2 and another 2 on top. That means that down on the bottom I can cut back on that power so that that denominator would be a 2 power of 13. Up on the top, the negative will change the order of this subtraction so that it would be a 3 power of 15 minus a 2 power of 15. And so we could go back over to our calculator and see what we can generate from that and verify that we get that correct numerator and denominator. 3 power of 15 minus 2 power of 15. And that should be that 143,16139. Down on the bottom, 2 power of 13. And that should be the 8192. And there it is, those two separate values. So while my calculator fortunately went ahead and created that fraction answer, just wanted to show you another little example of that tinkering that you could do in order to work that sort of stuff out, just in case there were any particular problems where you needed to do so. Geometric series can be bumped up from just partial sums to infinite sums or infinite series. What that would mean, though, is that we're going to be very limited to what kind of common ratios we're going to be allowed to handle. That last example there where our common ratio was a 3 over 2, if we just kept going and going and going, those terms would keep getting bigger and bigger and bigger. If I tried to consider the infinitely many terms that there are in an infinite series, that wouldn't converge. So I wouldn't be able to do an infinite series. I wouldn't be able to do an infinite sum. I can only do partial sums when my common ratio is bigger than 1, or I should rephrase that a little bit more carefully, when the absolute value of my common ratio is bigger than 1. That means my series, my terms blow up in my face. That's divergent. only when our common ratio, absolute value, is less than 1 will we be able to get our terms decreasing, 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 so that our series will converge and we would have an infinite sum. So that is a restriction. We cannot have an infinite sum, or we can actually just cut it down and just say the sum, unless our common ratio, absolute value of our common ratio, is less than 1. Now going back to that very first example, 1, 1/2, 1/4, 1/8. Common ratio we found was 1/2. Now the formula that we've got, very simple. The denominator is that 1 minus r. The numerator, as it turns out, completely goes away except for the first term. A little bit of niftiness that just kind of distills down so nicely for us. And so if we come back to that, use that formula, the sum of those infinite number of terms would end up being 2. This actually is, oh boy, I don't remember the name of it confidently. I want to say Zeno's paradox. If I try to, let's say, move from my current location to the door, and in doing so, I am able to close half the distance to the door, step after step. So from here to the door, I can get halfway there in my first step. Then my next step is halfway to the door again. That would be my second step. Then my next step gets me halfway to the door again for my third step. I have traveled half the distance, a quarter of the distance more, an eighth of the distance more. That actually would end up working out. I try to travel that distance, that one whole distance. The paradox here is that if I keep on taking half the steps that are half the distance, if I keep taking steps that are half the distance, then do I ever truly reach the door? Because each step gets smaller and smaller and smaller and smaller, technically speaking. I don't ever reach the door. Well, realistically, we know that that's not true, and so this only works in a certain sort of manner of thinking, but what that kind of idea generates is this connection between taking steps that are covering half the distance, 1/2, 1/4, 1/8, and that without that extra term in the front, my infinite sum would be 1. One length from here to the door. So I can reach the door, but I can't reach the door. That's the paradox. Anyways, little quirky side note. The sum. Again, they don't have to literally refer to infinite sum, infinite series. They could just say the sum. And by what they give you, the ... saying that never ends, so they've given it to you in kind of an under the radar fashion. 4, -12/7, 36 49ths, ... I have an infinite number of other terms that follow this particular pattern. What I need is the first term and the common ratio, and so like we've seen before, we're going to have that first term. Thankfully, that was just right there. It doesn't always have to be right there. Remember that they can be a little clever in trying to get you to come up with the first term. They could tell you things like the 10th term and the 5th term of a geometric series are blah, blah, blah. You could work that out based on the relationship. And so in this particular case, though, a lot more direct. The common ratio comes from our second term divided by our first term. -12/7 divided by 4 gives us a common ratio of -3/7. And so that would mean that, according to our formula, our first term is 4. That goes on top. Our common ratio is a -3/7. That goes on the bottom with a 1 minus the common ratio. So we would have, I'll tell you what, let's be lazy. I know that some of y'all are about that. So you'd be like
4 divided by parentheses 1 minus negative 3 over 7 parentheses enter. 2.8, well, that happens to be nice, but if we literally wanted a fraction version of that answer, 14/5. So, there we go.